So we've been talking about linear functions and linear equations. Now we're going to transition to quadratic functions and applications. So a quadratic function is a function of the form f of x is equal to ax squared plus bx plus c, where the leading coefficient a is not 0. So you want to make sure that this leading coefficient right here, a, is not 0. Now keep in mind a, b, and c are just real numbers and your variable is x, okay? So basically, notice that a quadratic function has power 2, all right? So basically, we've gone from degree 1 or power 1, that's linear, to power 2 or degree 2, which is now called quadratic, okay? So basically, we're raising the power on the variable. Now notice what would happen if your leading coefficient were 0. If a were 0, then you would have 0 times x squared, and this whole term would be 0, and you would be left with just bx plus c. In other words, if a were 0, then the highest, this whole first leading term would be gone, and the highest power would be 1, and then this would just be linear. We would go back to linear. So in order for this to be quadratic, degree 2, a must not be 0, or else this whole first term would go away. All right, to get started, let's graph the most basic quadratic function. The most basic quadratic function is basically just x squared. Now remember that, well, I would like to inform you that whenever you are graphing a quadratic function, any kind of quadratic function, the graph will be a parabola. A parabola is a U-shaped graph, so that's what this would be. Now, remember that whatever you square becomes positive. Whatever real number you square becomes positive. So for that reason, all of your output values will be positive values, because even if you plug in a negative number into your quadratic function, your output will always be positive because you're squaring. If you square 0, you get 0 in return, so then the quadratic function goes right through the origin, 0, 0. If you square the number 1, 1 squared is 1 times 1, which is 1, so 1 comma 1 is on the graph of the parabola. If you square 2, 2 squared would be 4, because 2 times 2 is 4, so it jumps up way over there. And of course, you can keep on going, right? 3 squared would be 9 way up here, 4 squared would be 16, even higher, and so forth. The other side of this curve, if you plug in negative 1 squared is negative 1 times negative 1, which is positive 1. Negative 2 squared is negative 2 times negative 2, which is positive 4. And of course, you can keep on going in that direction. So if you connect the points here with a smooth curve, what you get is a U-shaped graph, famously known as a parabola. All right, this is our most basic parabola. A few things I want you to notice is the lowest point on this parabola is right here. This is called the vertex. And the vertex is at 0, 0. So the lowest point is right here, right at the vertex. When we read the domain and the range for this quadratic function, remember that the domain is a set of all of your x values, whereas your range is a set of all your y values. The way you read your domain, all of this is really important here. The way you read your domain is from left to right. So you're asking yourself this question: how far left is this parabola going? And you should think, well, it's going forever to the left. In other words, it's getting wider and wider and wider. In the other direction as well, wider and wider and wider. Forever to the left, forever to the right. That must mean your domain is all real numbers. This is interval notation for all real numbers. Your range is a set of your y values, and that's read from bottom to top. The lowest y value is 0, and then there is no highest y value. It keeps on going up forever. So then it goes from 0 to positive infinity. It never stops rising. I have a bracket on 0 right here because 0 is actually located on the curve. It's one of your y values. Now, we have something called the maximum. The maximum is your largest y value. Sometimes instead of writing maximum, I say max for short. And then your minimum is your lowest y value, okay? Maximum is your highest y value. Your minimum is your lowest y value. Now, when you look at this parabola, what is the highest point? I don't care which side you look at. What's the highest point? You should be thinking there is no highest point. This parabola keeps on going higher and higher and higher. For that reason, you would say there is no maximum, right? This parabola has no maximum. I'm just going to say none. Don't say positive infinity because when you say a maximum or a minimum, we're looking for a real numbered value. And infinity is not a real number. So you're looking for a real number y value, a real number function value. There is no real number where this parabola says, that's it, that's as high as I'm going. No, it keeps on going higher and higher. However, for the minimum, again, remember you're looking for the real number y value that is the lowest one. It's right here. It's 0. That's the lowest y value. So then the answer here for your minimum is simply 0. You may want to add this to your notes that when we ask for a max or a min, we're looking for a real number y value, okay? All right. What I would like to do now is quickly take you through a few more functions. They're not quadratic, but a few more functions that you should know really well. F of x is equal to x cubed. This is the cubing function or a cubic function. It's basically your most basic cubing function or your most basic cubic function. Now, I'm going to show you a quick sketch of this graph. Forgive my quick sketch. It might look a little sloppy. Okay. All right. Remember, whatever real number you plug in to this function, you will cube it. Now, if I plug in 0, 0 cubed is 0 times 0 times 0, which is 0. So then this curve goes right through the origin. If I plug in the number positive 1, 1 cubed is 1 times 1 times 1, which again is just 1. So then this curve goes right through 1, 1. If I plug in 2, 2 cubed is 2 times 2 times 2, which is 8. And of course, you can keep going. Let's go in the other direction now, though. Negative 1. Negative 1 cubed is negative 1 times negative 1 times negative 1, which is negative 1. So negative 1 is on your curve. And then negative 2 cubed is negative 2 times negative 2 times negative 2, which is negative 8. So then this curve looks something like this. Okay? This is your most basic cubic function. Okay? Let's talk about domain, range, max, and min. Domain, range, max, and min. Remember that the set of your domain is a set of your x values. Remember that the range is a set of your y values. Remember that your maximum, which I just call max, and your min are real numbered y values, okay? A few other things. Remember that your domain is read left to right. Your range is read from bottom to top, okay? So let's talk about your domain. How far left is your branch going? Well, I know it's going down forever. That's kind of clear with this arrowhead. It's pointing down. But notice what the branch is doing. It's going further left, further left, further left. Eventually, it'll go this way forever. So it's going from negative infinity all the way to how far right is it going? How far right? It's going to go right all the way to positive infinity. So then the domain is all real numbers. Of course, you write that in interval notation as negative infinity to positive infinity. The range is a set of your y values. You read it from bottom to top. How low is this going? To negative infinity. How high? to positive infinity. So your range is negative infinity to positive. It's all real numbers, okay? Now, what is your maximum? What's your largest y value? None. Very good. And the same thing goes for your minimum, right? You have neither a max nor a min, because there is no y value that is the highest. There is no y value that is the lowest. It keeps on going down forever. It keeps on going up forever. All right, very good. The next function I'd like to make sure that we understand very well is the square root function. Now, I'm going to try to be smart as far as what I plug into this function. I want to plug in positive numbers only, because you can't really take the square root of a negative number, not in the real number plane. Because let me actually, before I draw my axes, let me actually talk to you just for a minute about what that square root symbol means, if you'll allow me. So this notation, the square root of 25, means what real number squared gives you 25? You should say 5, because 5 squared is 25. 16. The square root of 16 is asking you for the real number whose square is 16. That would be 4. You could keep going, right? And the square root of 9 means what real number squared gives you 9, which would be 3, and so forth. You know, you could also do this, folks, the square root of 15. Now, this is a problem because there is no rational number whose square gives you 15. In other words, this would have to be a little bit smaller than 4. How do I know that? Well, the square root of 16 is 4. Therefore, the square root of 15 must be a little bit less than 4. But if you punch this into your calculator, you're going to get an irrational number as a response. What do I mean by that? I mean, an irrational number by definition is a number that cannot be written as a quotient of two integers. Basically, it's going to be a decimal that never stops. It's just going to keep on going forever. So I'm going to say irrational. This is an irrational number, okay? So the square root of 15 is fine. You can plug in 15 if you want. You're just going to get a decimal that it keeps on going, and it's just going to be a little bit inconvenient when you go to graph, okay? The square root of 20, what is that? Well, that's also irrational. You cannot find a rational number whose square gives you 20. So I want to stay away from 20. So then what kind of numbers am I wanting to plug in? Well, numbers like 25, 16, and 9, these are called perfect squares. So when I consider input values, I only want to consider perfect squares, okay? Another thing I want to stay away from are negative numbers, because imagine this. What real number squared gives you negative 16? You should say nothing, because no matter what real number you square, you should get a positive number. So there is no real number such that when you square it, you get negative 16, because whenever you square something, it becomes positive. So this is kind of impossible in the real number system. So I'm going to say this is not a real number, okay? Not a real number. So I want to stay away from numbers that are not perfect squares, just for convenience sake, and I want to stay away from negative numbers as my input. That leaves me with positive numbers that are perfect squares. All right, the first number I'd like to evaluate is, or the first value I would like to evaluate is f of 0. So f of 0 would be the square root of 0. What number squared gives you 0? 0. 0 squared is 0. So 0, 0 is on the graph of my curve. 1. The square root of 1 would be 1, because 1 squared is 1, right? 4. I'm going to jump over to 4 on the x-axis. When I plug in 4, the square root of 4 would be 2, because 2 squared gives you 4. Next would be 9. The square root of 9 would be 3 because 3 squared is 9. And of course, you can keep on going, but I think this is enough points for us. So the curve looks like that. Remember, it does not keep on going over here. It begins, if you will, at 0, 0, and it goes like that, upward. All right, so let's talk about domain, range, max, and min. Now remember, domain is read left to right, and it's a set of your x values. So the x value that is furthest to the left is 0, and then it keeps on going to the right forever, so it's all the way to positive infinity. So in interval notation, the domain would be a bracket at 0 all the way to positive infinity. The range is a set of your y values. You read it from bottom to top. Your lowest y value is 0, and it goes up forever eventually, so from 0 all the way to infinity. It'll be written the same way as the domain. Okay? It's written the same way, but remember, these are x values, whereas these are y values. Now the max, you don't have a max because the range just keeps on going up forever, right? It keeps on going up forever, so you have no max. But when it comes to a minimum, you do have a minimum. This is your lowest y value. It's right here at 0. That's what you already said in the range. Your lowest y value is 0. So I'm going to write that in, okay? All right, very good. Let's go to your next function. The last function I'd like you to be really familiar with is the absolute value function. Now, remember that absolute value of a number means its distance from the origin. How far away are you from the origin, okay? So let's go for it. Because distance can never be negative, you know that the absolute value of a number will always be positive. So regardless of what your input is, whether it's negative or positive, your output will always be positive. That forces us to be in either quadrants 1 or 2. I'm going to scale out my axes a little bit here. That'll be good enough to get an idea of what this graph looks like. All right, let's start plugging in some points. The absolute value of 0 is 0. Basically, when you're standing at 0, how many units away from the origin are you? 0 units away. So then the absolute value of 0 is 0. The absolute value of 1 is 1, because that would mean you're 1 unit away from 0, or from the origin. So the absolute value of 1 is 1, 1 comma 1. The absolute value of 2, that's saying how many units away from the origin are you? 1, 2. So the absolute value of 2 is 2. The absolute value of negative 1 is 1. The absolute value of negative 2 is 2. So this shape here is a V-shaped. All of your absolute value functions are V-shaped. This is the most basic absolute value function. All right, let's talk domain, range, max, and min. How far left is this going? To negative infinity. How far right? To positive infinity. So the domain is all real numbers. Your range, how far low is this going? To 0. How high? Positive infinity. So basically all positive real numbers. Your max, there is no max because this V keeps on going higher and higher and higher. So you don't have a maximum. Your minimum, your lowest y value is 0. All right, everybody, these are the, let's see, how many functions did we go through? 4. The most basic quadratic function, cubic function, square root function, and the absolute value function. So 4 functions that I want you to know really well. Now I want to discuss a very important topic called transformations. For this section, I want to focus on 4 different types of transformations. The horizontal translation, you can also call it a horizontal shift, a vertical translation or vertical shift, and a vertical stretch or a vertical shrink, and then a reflection across the x-axis. All right, check out this example. Graph g of x is equal to x plus 2 quantity squared minus 3 by first graphing its parent function Then use transformations to graph function g. State the domain, range, maximum, and minimum of function g. Now, first things first, let's figure out what the parent function is. Now, the first four functions I introduced to you in the first part of this lesson are four of your parent functions. So you have the quadratic function, which is a squaring function, your cubic function, absolute value function, and the square root function. Which one of those four is the parent function for g? Because I see this function g being squared, that must mean the most basic squaring function, the most basic quadratic function, is my parent function. And again, I know this because I see this being squared, so then the squaring function must be my most basic, must be my parent function, okay? So what I'm going to do is I'm going to start by graphing this parent function. We just finished graphing it a few minutes ago. You know what it looks like. It's a parabola, right, whose vertex is at the origin. So here's that same parabola that you and I graphed just a few minutes ago. It's the same one. It's the most basic parabola, right? Now what's going to happen is, the idea with transformations is, the graph of g will be identical to the graph of f, except it will be transformed or moved in the plane. Now this plus 2 here moves your parabola to the left 2 units. It's a type of horizontal translation. I know it's a horizontal translation because, listen carefully, this plus 2 is written within this squared expression. It's part of what is being squared. It's inside of the parentheses. That's what makes this plus 2 a horizontal translation. You see this minus 3? That's outside of the parentheses. It's outside of the squared expression, and that's what makes it a vertical translation. All right, so this plus 2 represents a horizontal translation 2 units to the left. Hey, by the way, if it had said x minus 2, it would have been 2 units to the right. This is a vertical translation, 3 units downward. It's going down because it's negative. Had it been a plus 3, it would have gone 3 units up. So the idea is, we're going to take this curve, this most basic parabola, and we're going to move it 2 units to the left and then 3 units down. All right, I'd like to start with this point here. Let's move it 2 units to the left and then 3 units down. That drops you off at -2, -3. Right there. Again, that was 2 units to the left, 3 units down. Okay, that's the movement. Let's go for another point. This point here, -1, +1. 2 units to the left, 3 units down. Drops you off at -3, -2. About right there. Again, that was 2 units to the left and then 3 units down. Next point, -2, +4. 2 units to the left, 3 units down. Drops you off at -4, -1. I'm sorry, -4, +1. You know, if you have graph paper, that would be best here. Even better than what I'm doing, right? 1, 1. 2 units to the left, 3 units down. Drops you off at -1, -2. Finally, 2, 4. 2 units to the left, 3 units down. Drops you off right on the y-axis at 0, 1. So when I graph this parabola here, it's the same parabola that we've had before. It's just that the parabola is moved over in the plane. Okay? This red parabola, which I call my parent, it's the same as the green. The only difference is that it got moved over 2 units to the left and then 3 units down. Okay? Let me fix this point here. Seems like I was a little sloppy. Let's get the domain, range, maximum, and minimum of function g. All right, domain is going to be all real numbers, because this parabola is still, even after those transformations, is still expanding forever to the left and expanding forever to the right. The range, however, is going to be different. The lowest y value is now -3. Look at this. It's not coincidence that the minimum is -3 and I had a -3 right there in my function. You see that? -3 and then all the way up to positive infinity. Okay? So from -3 is your lowest y value all the way up to positive infinity. We just said, did you hear me say that? That -3 is your lowest y value. That must mean your minimum is -3 because that's your lowest y value. Now this parabola keeps on going up and up and up and up and up forever. That means you do not have a maximum at all. Good job, guys. Let's do another couple examples of transformations. All right, everybody, check this out. Graph function h 2 times the absolute value of x minus 1 plus 1 by first graphing its parent function. Then we'll use transformations to graph function h. And then when we're done, we'll state the domain, range, max, and min for function h. Now, it's important that you and I identify what the parent function is. When you look at function h, you don't see anything being squared. So the parent function is not the squaring function. It's not the quadratic. Instead, what I do see are absolute value bars. So the absolute value function is my parent function. So I have my parent function. You remember what it looks like? It's that V-shaped, where the lowest point of that V is at the origin. Now, there's 3 different types of transformations in function h. I already taught you this transformation and this one out here. This one is going to be a horizontal translation because it's within the absolute value bars. Because the -1 is inside of the absolute value expression, that's what makes it a horizontal translation. Now this time it'll be 1 unit to the right. This +1, however, is outside of the absolute value bars. It's outside of the absolute value expression, and that's what makes it a vertical translation. This time, 1 unit upward because it's a +1. I'll talk about this too in just a second. All right, so we have those 2 labeled there. 1 unit to the right, and this one represents 1 unit up, okay? Now this 2 here in front of the absolute value bars, basically the coefficient of these absolute value bars, is what it represents a vertical stretch. Now, because this number is greater than 1, it represents a vertical stretch. Had this number been a fraction, something less than 1, then it would be a vertical shrink, okay? But it's a vertical stretch here because it's more than 1. Now we say it's a vertical stretch by a factor of 2. So the way you're going to apply that vertical stretch is by taking all of your y values and doubling them. I'll show you how to do this. Okay, you can see the first thing I did was graphed the parent function. Now the parent function is that V-shaped. It's the same exact V that you and I graphed earlier in the lesson. Now what I need to do to this V is move it horizontally 1 unit to the right. I need to stretch it by a factor of 2, and then I need to do a vertical translation 1 unit up. I want you to catch the order. Please add this to your notes. When you have multiple transformations, this is what the order that you should follow. Do your horizontal translations first. And then if you have a vertical stretch or a vertical shrink, do that next. You have one or the other here. And then do a reflection. The only kind of reflection that you and I are studying at the moment is a reflection across the x-axis. I have yet to show you what that looks like. And then a vertical translation will always come last. Okay, everybody? For the sake of this lesson and for the sake of our course, I'm going to stay away from, I'm going to skip over the vertical shrink. I'm only going to focus in this lesson on a vertical stretch. Okay, everybody? Vertically stretching something. Maybe if there's time toward the end of the course, we can talk about a vertical shrink. But at this time, I'm only going to focus on a vertical stretch. All right, so here we go. We're going to take this V. We're going to move it 1 unit to the right, stretch it by a factor of 2, and then 1 unit up. All right, let's do this together. Are you ready? Let's do this point first, 0, 0. The first thing I'm going to do is move it 1 unit to the right. That leaves me at 1, 0. In order to, I'll keep my cursor right here where we're at, okay? 1, 0. In order to stretch by a factor of 2, I take the y-coordinate and I double it. I multiply it by 2. But the y-coordinate here is 0. And 0 times 2 is still 0. All right. Now 1 unit upward. There. 1, 1 is the final resting place. Okay? Let's go to the next point. How about this point here, which is 1, 1? I'm talking about the point that's on my parent function. 1, 1. Let's move it 1 unit to the right. That drops me off at 2, 1. 2, 1. Now it's time to do the vertical stretch by a factor of 2. I'll take the y-coordinate, which is 1, and multiply it by 2. 1 times 2 is 2. So then now we're up here at 2, 2. And then don't forget, you have to vertically translate it 1 unit up. So 2, 3 is my final resting place there. 2, 3. Let's go for this point. 2, 2. 1 unit to the right. That's 3, 2. 3, 2. Now vertically stretching it by a factor of 2, you're going to multiply your y value, which is 2, by 2, which will give you 4. So 3, 4. All right, 3, 4. But don't forget, we have to vertically move it up 1 unit. So finally, it's at 3, 5. Okay, 3, 5. Maybe about right there, give or take. So our v is looking like this so far, okay? Let's not forget to do these ones over here. -1, +1. 1 unit to the right puts you at 0, 1. When you double that y value of 1, you're at 0, 2. And then when you move it up 1 unit, you're at 0, 3. All right, last one here. -2, +2. When you move it 1 unit to the right, you're at -1, 2. When you double that y value, you're at -1, 4. And then finally move it up 1 unit, -1, 5. Okay, so the other branch looks something like this. So this is my v for function h, okay? So that was 3 transformations in 1. Let's get the domain, range, maximum, and minimum for function h. So look at the yellow graph. How far left is it going? Forever. How far right is it going? Forever. So therefore the domain is all real numbers. The range, bottom to top. What's your lowest y value? It's right here at 1. So it starts at 1, and then the v keeps on going up forever and ever and ever. Notice what you just said. The lowest y value is 1. That means your min is 1. Your minimum value is 1. Notice that that +1 is written right there. Interesting. Now, because the v keeps on going upward forever, there is no maximum. Okay? Good job, everybody. There's only one other type of transformation that I want to teach you, and that is the reflection. Check this out. Graph function r, which is negative square root of x plus 2 by first graphing its parent function, and then we'll use transformations. All right, everybody. The action that I see in my function is this square root. So because I see a square root, that means the most basic square root function is my parent function. All right, so I have my parent function identified. Now let's talk about transformations. We've talked about this already a few times. Since the +2 is within the square root expression, since it's within the action or the argument of the function, this +2 represents a horizontal translation, 2 units to the left. Now, what we're talking about for the first time here is this negative represents a reflection across the x-axis. And so what that means is whenever you have a negative as the coefficient, whenever the coefficient here is negative, that represents a reflection across the x-axis, which just means the x-axis is like a mirror, mirroring whatever you see on one side of the x-axis to the other. All right, folks, I have this parent function back on our plane. I have the graph here, the same graph that you and I plotted earlier in this lesson. I've labeled it F as well to be really clear. Now, what I'm going to do to this curve is move it 2 units to the left, and then I'll reflect it across the x-axis. Let's go at this point first. 2 units to the left drops me off here. When I reflect this point across the x-axis, all I have to do is take the opposite of my y value. But wait a minute, my y value at this point is 0. This point is -2, 0. And the opposite of 0 is just 0. So then, when I reflect it, it stays right where it's at. Let's try this one. This is 1, 1. When I move it 2 units to the left, it becomes -1, +1. When I reflect that across the x-axis, it becomes -1, -1. All right? I took the opposite of my y value. Finally, this is 4, 2. When I move it 2 units to the left, it becomes 2, 2. When I reflect that across the x-axis, it becomes 2, -2. Again, just negate or take the opposite of your y value. So then the curve now looks like this, everybody. This is the curve for function r. Now let's get the domain range max and min for function r. All right, remember domain from left to right. So from here all the way to the right. So that means from -2 all the way to +infinity. From -2 all the way to +infinity. Remember your range is read from bottom to top. How low is this curve going? Well, it's going down forever, right? Eventually, it's going down forever. So from -infinity all the way up to this point here, be careful. We're talking about range. And range is a set of your y values. So what's the y value right here? 0. Don't say -2. The y value is 0. So from -infinity all the way up to 0. All right, so from -infinity all the way up to 0. Be careful that you take the y value at this location and not the x value. All right, cool. You just finished saying that the highest y value is 0. That must mean the maximum is 0. And then you just said that you just finished realizing or inspecting that this curve keeps on going down forever. That must mean there is no minimum. All right, cool deal, everybody. Now, all of the transformations for the quadratic function can be summarized in this form here. Let me break this down for us. All right, the coefficient a here will tell us a lot about the parabola. Yes, this is a parabola because this is being squared. Now, what I want you to write down is if a is positive, the leading coefficient is positive, the parabola is opening upward. If a, the leading coefficient, is negative, the parabola is opening downward. This is how I say a is positive. It's greater than 0. This is how I say if a is negative, it's less than 0. Okay? Now, if the absolute value of a is greater than 1, then the parabola will be more narrow than its parent graph, right? That most basic parabola. If the absolute value of a is less than 1, then the parabola will be wider than the most basic parabola. All right, let's keep on going and breaking this down. Now, what's interesting is the vertex, which is sometimes the lowest point on the curve or the highest point on the curve, the vertex will be at h, k, h, k. The axis of symmetry, now a little bit about the axis of symmetry, it's a vertical line about which your parabola is symmetric. Let me show you a picture of what I just said. So if you have a parabola here, let's see, let me draw it like this. If it's opening upward, then your axis of symmetry is something like this. It cuts your parabola right in half, and what you see on the left-hand side is mirrored on the right. But the interesting thing is the AOS, or axis of symmetry, is a vertical line that goes right through your vertex. So the AOS will always have the equation x equal to, because it's a vertical line, x equal to this first coordinate, x equal to h. All right, cool. Let me show you a few quadratic functions that are written in this form, and let's see if we can graph it. All right, here we go, everybody. Now, we know that the parabola is going to be more narrow than we're used to because of that factor of 2. All right, so just keep that in mind. Now, the first things first, I want to know, does this parabola open upward or downward? I hope you said upward because the leading coefficient is positive. All right, that's great. Now, let us identify the vertex and the AOS, the axis of symmetry. Now remember, your vertex is h, comma, k. Here is your h value. It's the number, now this is tricky, it's the number that follows the subtraction sign. So if I kind of cover up the subtraction sign here, like that, what number do you see? 1. You know what I usually tell my students is, in order to identify the correct h value for your vertex, always take the opposite of what you see. Because this is x minus 1, the vertex will be positive 1 for your h value. So positive 1 and then negative 3. Take exactly what you see out here. So h, comma, k, positive 1, negative 3. Now that the vertex is found, remember your AOS is just the vertical line that goes right through your vertex. Vertical line, that means it has to be of the form x equals, right? So it's going to be x equal to the first coordinate in your vertex. So I kind of like to tell my students that you get 2 for 1 here. If you know the vertex, then you automatically know the AOS. Let's plot what we have so far. The first thing I'll plot is the vertex, 1, negative 3. And remember that the AOS goes right through your vertex. It's a vertical line that goes right through your vertex. Now remember, the AOS is not part of your graph. It's not part of your parabola, but it does help you get your parabola, okay? Now, this is all we have so far, guys, and we know it's opening upward from this vertex, right? What's going up. What would be really nice is if you and I grabbed a couple more points. So I want you to find 2 additional points. Now this is the rule of thumb, okay? This is the idea. Plug in something for x, right? Plug in something for x that is close to your vertex and your AOS. So the AOS and the vertex goes right through x equal to 1. So plug in an x value that's close to 1. You can plug in whatever you want, guys, but I think it's a good idea to plug in either 0 or plug in 2, either one of these. Let's plug in 0, shall we? Let's do f of 0. All right, f of 0, okay? It's going to be 2 times 0 minus 1 squared minus 3. We have some arithmetic to do. Okay, so this turns out to be 2 times positive 1 minus 3. This turns out to be negative 1. So the ordered pair here is 0, negative 1. 0, negative 1. I want you to watch this. This is, what I'm about to show you next is the beauty of the AOS, the axis of symmetry. I asked you for 2 additional points. One of them you found right here by plugging in 0 and getting negative 1. I don't want you to have to do that again. I want you to use symmetry. Remember, AOS stands for axis of symmetry. I want you to use symmetry to get another point. And this is how. I want you to get the mirrored image of this point across the AOS. Remember, the AOS is like a mirror. It cuts your parabola in half. What you see on the left-hand side, you get over here on the right, the mirrored image on the right. So if this point, watch this, is 1 unit away from the AOS, right? If this point is 1 unit away from the AOS, that means there's another point on this side that's 1 unit away. Well, that would be what? 2, -1. That's the mirrored image right there. We found that point using symmetry, and that's what I'm going to expect you to do. Okay, 2, -1 found by using symmetry. So that's the idea, folks, and that is the beauty of having this quadratic function written in this form. You can quickly see what the vertex is, and you can see what the AOS is, and it doesn't take that long to get the graph of the parabola. Let's do another one. All right, check out this brand new function, function f, negative x plus 2 quantity squared, and then plus 1. All right, first things first, is this parabola going upward or downward? I hope you said downward because the leading coefficient is negative. All right, cool. Now that we know it's opening downward, let's move toward finding the vertex or identifying the vertex and the AOS, okay? So let's find both of those. Now, because this function is written in this particular form, we know what the vertex is. The vertex is h, k. H, k. Do you remember what I said about h, identifying h correctly? Take the opposite of what you see. So you see x plus 2, so therefore your h value is -2. Be careful there. So then the vertex starts with -2. And then as far as your k value is concerned, take exactly what you see, which is +1. Okay? So that's the +1 right there. Now your AOS is the vertical line about which your parabola is symmetric. So it's x equal to that first coordinate in your vertex, x equal to -2. All right, let's graph what we have so far. The first thing I'll do is plot the vertex, which is -2, +1, which is right there. And then your AOS, remember the AOS is this vertical line that goes right through your vertex, cuts your parabola in half, if you will, like this, okay? All right, so this is all we have so far. We know it's opening downward from that vertex, okay? Let's find a point. 2 additional points. I recommend that you plug something into this function for x that is close to your vertex and AOS here, all right? So plug in a number an x value that is close to -2. So I suggest -3 or -1. Remember, you can do whatever you want. You can plug in whatever you want, but I suggest -3 or -1. I'll go with -3. All right, so when I plug in -3, I get negative, and then -3 plus 2 squared, and then plus 1. So it'll be, don't distribute this negative on the outside, okay? So negative, and then -3 plus 2 is -1. This is me following the order of operations. Don't make these two negatives become a positive. That's out of order. You got to square -1 first, which is +1, and then plus 1. So this is basically -1 plus 1, which is 0. So then the ordered pair you and I just generated is -3, 0. -3, 0, which is right there. Now, the second point that you and I generate will be found by using symmetry. If -3, 0 is on your parabola, then -1, 0 is also on my parabola. I found that using symmetry. All right, so the parabola looks something like this then. All right, everybody? Cool deal. All right, now this is what's coming down the pike, okay? Graphing quadratic functions is somewhat fun and it's great, h comma k, got it, when it's of this form. But what happens when it's not in this form? Well, if it's not written in this form, we don't know what the vertex is, which is a big problem. I'm going to show you two different ways to find the vertex when it's not written in this form. All right, everybody, here's the quadratic function. All right, and I'm going to show you two different ways to find the vertex. Okay, two different ways to find the vertex for this quadratic function. Method number one is to complete the square in x so that we can rewrite it, the function. All right, so what I'll do is I'll complete the square, and what I'm going to do is I am going to add a number to this function. All right, I'm going to add a number, and this is the number that I'm going to add. This is how you complete the square every single time. I want you to take half. Well, first of all, let me say this. Before you can complete the square, the leading coefficient has to be positive 1. Good news for this problem, the leading coefficient is already positive 1, so we have the green light, if you will, to complete the square. Again, leading coefficient has to be positive 1. It is, so we're ready to go. So what we're going to do is we're going to take half of the coefficient of the first degree term. All right, this term here is degree 2. This term here is degree 1, first degree. So the coefficient of the first degree term is -6. Take half of -6. Half of -6 is -3. Now take -3 and square it, and you get 9. So then this is, right here, the number that I want you to add to your function, okay? So add a 9 right here, okay? Don't forget about this plus 8. You have to bring it down, okay? Now, by you adding 9, you just changed your function. We didn't want to change the function. To counter that adding of 9, let's subtract 9 at the same time. If you add 9 and subtract 9 at the same time, well, those 9s cancel each other out, and you're left with the same function, which is a good thing, the same function that you started out with. So whatever you add, you must subtract it at the same time so that your function remains unchanged. All right, let me create some space for us here. So what this does for us is creates a perfect square. F of x, this much right here, these three terms can be written as x minus 3 quantity squared, and then 8 minus 9 is -1. Okay? All right, everybody. I want to remind you that whenever you have a trinomial, three terms, and it's a perfect square, right? I know this is a perfect square trinomial because we completed the square. It always factors as a square of a binomial, a square of two terms, okay? So 8 minus 9 is -1. Now that I've done that, oh, by the way, if you were to expand this, x minus 3 squared, you would get x minus 3 times x minus 3. And if you distribute, which some people know as FOIL, you will get these three terms right back, okay? Sometimes students ask me, wait, where did the -6x come from? If you were to distribute this, x minus 3 times x minus 3, like this, right? X minus 3 times x minus 3, and then distribute, some people know that as FOIL, you'll get x squared minus 3x, another minus 3x, and then plus 9. And your -6x that you see right here, and some people say, where did that go? I don't see it anymore. It's right here. -3x and -3x make -6x. Okay? So it's all there in that factored form. Okay? So this is called factored form. All right, very good. So now that you completed the square and you rewrote the function, now you can identify what the vertex is. The vertex is h comma k, so I'll just put v for vertex, and it's +3, -1. Cool deal. So that's how you find the vertex using method number 1. Now let me show you method number 2. Method number 2 is a formula. It's a formula for finding the vertex every single time. So this is the formula, and then once I write it down for you, I'll explain it. Negative b over 2a, comma, f of negative b over 2a. That's the vertex formula. Okay? So this is what your vertex will be every single time. So let me remind you, when you have a quadratic function, this is your a value is your leading coefficient. So your a value is your leading coefficient, which is positive 1. Your b value is the coefficient of the first degree term. So in this case, your b is negative 6. And your c value is your constant term, all right? So when they're calling a out and b right here, they're talking about the leading coefficient is a, and b is the coefficient of your first degree term. So let me see if I can illustrate this for you. Negative b over 2 times a would be equal to negative, and then what is your b value? Your b value is negative 6. So it'll be negative 6 over 2 times a. A is your leading coefficient, which is positive 1, like that. All right, simplify. Positive 6 over 2, so then this is 3. Now the vertex, keep that in mind, folks. Everybody just kind of, maybe we'll circle that. Now the vertex formula says whatever negative b over 2a turned out to be, plug that number into f. So let me do that now. So f of negative b over 2a will be f of 3, because that's what negative b over 2a turned out to be. So I'm plugging 3 into my function. So I'm going to get 3 squared minus 6 times 3 plus 8. Do this arithmetic. It'll be what? 9 minus 18 plus 8. So all of this gives you negative 1. So you can see that the vertex then is, I'll scoot this up a little bit here, your vertex is 3, comma, negative 1. So there's 2 different ways to find the vertex. Either complete the square or use the vertex formula. Up to you. Let's try another example. Find the vertex of this function. Let's do it both ways, just because we're still learning each of the ways, all right? So let's try method number 1. Now, method 1 is us completing the square, okay? Now, do you remember me saying that the leading coefficient has to be a 1 before you complete the square? Well, the leading coefficient here is not 1, it's 3. So I'm going to show you how I get around that. So here, I need my leading coefficient to be a 1. So what I do is I factor that 3 out of my first 2 terms. I factor the 3 out of my variable terms. Just my variable terms. All right, like that. You know we're correct because if you distributed the 3 back in, you'll get the original function back. Now your leading coefficient is positive 1 and you're ready to complete the square. Remember how you complete the square. You take half of the first degree term. Now be careful. The first degree term, the coefficient of the first degree term is 4. Don't take 12. Look at this term. Okay, half of 4, of course, is 2. And then we square 2, which is 4. So what I'm going to do is I am going to add this number, 4, inside the parentheses. All right, now remember, whatever you add to your function, you must subtract it at the same time to counter that, all right, so that your function remains unchanged. Be careful. We're not going to subtract 4. I know we just wrote plus 4, so you might be tempted to say, okay, let's subtract 4. But in reality, because there's a 3 out front, you've really added 3 times 4. 3 times 4. Right? Everything inside the parentheses is being tripled. So you've really added 12. so we want to subtract 12 at the same time. That could be tricky, so be very careful there, all right? Now that we've completed the square, we can factor that trinomial, that three-term polynomial inside the parentheses. It'll factor as a square of a binomial every time. On the outside, 13 minus 12 is just positive 1. Now, and here, the variable is x, so that's what I'll write. And then this middle term, oops, sorry, I didn't mean to do that. This middle term is positive, so then this will be positive. And then this number here will be the number whose square gives me 4. What number squared gives you 4? 2, that's right. All right, we did it. We completed the square. So therefore, your vertex is negative 2. Remember, take the opposite of what you see. Negative 2, positive 1. There it is. All right? Let's find the vertex again, but this time using the vertex formula, which is method 2. Now remember the vertex formula is negative b over 2a. All right, so here we go. Negative, and then your b value is 12. Your a value is 3. So then this turns out to be negative 12 over 6, so negative 2. The next thing I'll do is I'll take negative 2 and plug it in to my function. And now just do a bunch of arithmetic. Be careful to follow the order of operations. So all of this gives you 1 when you do the arithmetic. So then your vertex is negative 2, positive 1. Okay, everybody, let's graph this function. All right, so now we're going to get back to graphing a parabola. What we need to do is find the vertex, okay? But before we do that, I wonder if you and I can determine whether this parabola opens upward or downward. Because the leading coefficient is negative, you know the parabola opens downward. All right, let's find the vertex. Once you find the vertex, you can find the AOS. How are you going to find the vertex? Well, you have a couple options. You can either complete the square or use the vertex formula. It's up to you which method you'd like to use. Now, for the sake of this video, I hope you don't mind, I am going to use the vertex formula to find the vertex. All right, so I'm going to do negative b over 2a. And in this case, it'll be negative, and now my b value is 12, my a value is negative 2. So then I get 12 over 4, which is just 3. All right? Keep in mind that these two negatives cancel out to be a positive. And now what I'll do is I'll plug 3 into my function very carefully. Do the arithmetic, and you get 3 squared is 9. 9 times negative 2 is negative 18. I'm trying to be very careful here. 12 times 3 is 36, minus 9. So when you do all of this arithmetic, you get 9. Yeah, 9. All right. Positive 9. So then the vertex can be written as, let's see. So we got 3. So let's write that first. That's our first coordinate here. All right, 3, comma, and then 9. Remember, your AOS is that vertical line that's going right through your vertex, so it's x equal to 3. All right, the parabola is opening downward, and we have our vertex and our AOS. Let's graph what we have so far. Okay, everybody, I have 3, 9, our vertex, plotted, and our AOS. All right, we know it's opening down. What would be really nice is if you and I can generate 2 additional points. One of them, I'll just choose an x value that's really close to my AOS. So I'll plug in either the number 2 or the number 4. Okay, I'll plug in either one of these numbers in, and then I'll use symmetry to get that second point. All right, I'm going to go ahead and plug in 2. So I'm going to do f of 2. So it's negative 2 times 2 squared plus 12 times 2, and then minus 9. So we got some arithmetic to do. Be careful here. 2 squared is 4. 4 times negative 2 is negative 8. We got plus 24 here, and then minus 9. When you do all of this arithmetic, you get, let's see, negative 17 would be these two, negative 17, and 24 would be 7. So then the ordered pair that you and I just generated is 2, comma 7, which is about right there, everybody. So there's that branch there. Now I can use symmetry to find an additional point. This point 2, 7 is just 1 unit from the AOS. That means 1 unit on the opposite side, I get another point, which would be 4, 7. About right there. So something like that. Remember, this is a sketch. All right, everybody. All right, everybody, this is a long lesson, so I'm going to end it here. I hope you learned a lot. You may want to watch or listen to a couple of the parts more than once just to make sure you have it. This is the end of this lesson, and I'll catch you in the next one, which is 1.4. All right, see you later.